All right, guys, so we're going to start topic 2. And this topic is going to go over everything that has to do with stress and strain for different types of materials and how we can use stress and strain and these different properties to help us solve for the future problems in this class. So this topic is a little bit different than what we have previously done, and it's a little bit different than what we're going to be doing later. There's a lot of terminology, a lot of names that we have to kind of remember. And what I'll do is after this, I have a Jeopardy that I put together. It's meant to be an in-person activity, but I can just upload that so you can use it to kind of test yourself and make sure that you're getting the objectives and the key terms for this topic, okay? So the first thing that we're going to talk about are tension and compression tests. So the idea here is if we want to measure the strength of a certain material, okay, there are different ways we can do that, but one of the most common ways of doing that is by doing a simple tension or compression test or tension and compression test. And what that basically means is we would either apply, like I'm going to draw a member here, we would apply tension to this, let's say this is a steel bar. We would apply tension at some force P, and we keep increasing P until we determine what the ultimate strength of this material is. We kind of record that, and this is like a lab test that we would do. So when you guys get to take this lab, hopefully it's in person, you'll get to see this kind of test. The other test is exactly the way it sounds, which is where we apply some compression to this bar, and we see how much this bar can handle in compression. Okay, so the way we do this again is through experimentation. Okay. What we do is we use tension and compression tests to determine the relationship between our average normal stress, sigma, and our average normal strain, epsilon. So let me write those down. Sigma and epsilon for different materials. And we're going to talk a lot about the relationship between sigma and epsilon, and it's going to be a relationship that we use very often and that you've probably been exposed to before. Okay, so before we get into that, let's talk about a conventional stress-strain diagram. Okay, we use stress-strain diagrams here to understand the full relationship between stress and strain for a given material. And I'm going to draw just the axes here so you can see we always put the strain here on the x-axis and the stress here on the y-axis. Okay, and what we're going to do is we're going to talk about several important features of these diagrams. Okay, the first thing we want to know, so we usually just, you can call this a stress strain diagram. We can abbreviate it like this. Okay, some things that we want to know that we remember from topic 1 is that sigma is equal to force over the cross-sectional area, and that epsilon is equal to, I'm going to call it delta over LO. Delta is just a change in length. You can call it L final minus L initial. Whatever you want to call this, it's just the change in length. Okay, and I'm going to add something here. I'm going to call this AO. And the reason for that, let me write down what it is and then I'll explain it. A naught is the original undeformed cross-sectional area. And the key word here is undeformed, because what happens is when we apply tension or compression to a member, we're increasing or decreasing its actual area, its cross-sectional area, right? So let me give you an example of that. If I were to pull on this bar, and the bar increases in length, it's actually going to stretch like this. And when I make a cut, this cross-sectional area is different than this cross-sectional area, the original one. So we always, because we don't want to kind of get into having to determine the new cross-sectional area, we're always going to be using the original cross-sectional area. And the deformation, again, for engineering applications is so tiny that this doesn't really make a big difference, okay? So what I'm going to do, I'm going to draw the tensile stress strain diagram for typical steel, and I'm going to go over each part of that diagram with you. Let me put it here on this page. Okay, so this is kind of like a case study. So the case study here is going to be steel, and it's going to be in tension. Okay, and this is to better understand the stress strain curve. So I'm going to start here with my y-axis, my x-axis, where I'm going to put epsilon, the strain, sigma, the stress. Okay, so here, let's start drawing. The first portion, I'm going to draw the curve, and then I'm going to tell you what each region is. So the first portion, the first point here, we're going to start at 0. What that means is, if I have 0 strain on the object, 0 elongation, I have 0 stress, right? So that's a point, that's 1 point. Nothing's happening in terms of stress, nothing's happening in terms of strain. So we're going to have something that looks like this. We just have a linear relationship, and I'm going to talk about that linear relationship after I draw the whole diagram. After some point here, which we call the yield point, okay, we have a period where, although I'm increasing the strain on the material, it's deforming, I am not increasing the normal stress. It's remaining the same. Then when that period is over, which we call yielding, I have something that looks like this until I reach this point of ultimate stress, and then I eventually reach some point of failure. Okay, so I'm going to go over each one of these parts. Let me just get my diagram in order. I'm going to section off all these parts. Okay, so this first section here, I'm going to call this section 1. We call this the elastic region. Okay, so we call this the elastic region because no matter what force I apply on the object, so let me actually draw the object that would go with this stress strain diagram. This is a bar, let's say, and this is a steel bar, and I'm pulling it, some force P. So it's in tension, and this is the tensile stress strain diagram for this bar, okay? So what's happening is this elastic region here means that no matter what force I apply in the elastic region, if I remove that force from the object, I will bounce back to the original position. So what you want to think about is what's something that's elastic, right? Like a rubber band or a hairband or something similar of that nature. Okay, you can also think of it in terms of like a gummy worm. I can stretch that gummy worm, I can make it longer, and I can remove my hands from the gummy worm and it'll kind of snap back to its original position and it won't have any permanent deformation. Okay, so that experience, that region experiences elastic behavior. Okay, so here I'm going to write some notes about elastic behavior. Okay, so straight line kind of doesn't make sense, but the curve is actually a straight line. Okay, which means that stress is proportional to the strain. We call this region linear elastic, and this is a very important term that you'll see in a lot of other classes. Okay, now what we have here is we have a point that's right after, directly after this point here, almost on it, that we call the yield stress or yield point. Okay, And that would mean that this here would be yield stress. Okay. We also have a point right before the end of our elastic region, which we call the proportional limit. Okay. And this is basically the first point where we can see some slight deviation from linearity, okay? For the purposes of this class and for most other classes, these 2 points are so close that we just assume that they're at the same point, okay? So I'm going to put here, let me rewrite this. This is just to make our lives a little easier, okay? So basically, and then just so we know what the proportional limit is actually, I'll say this is the proportional limit, first sign of non-linear behavior, okay? So that takes us into our second region here, which is, I'm trying to find another color I can use for all these regions, yielding. Okay, so yielding is this entire portion where we basically have an increase in our strain, but we don't have any increase in our stress, okay? So let's come over here. Okay, so it's an increase above our elastic limit, which means the last point of our linear elastic region. Okay, and this is the first point that we see permanent deformation. This is very important. So what does that mean? Let's say you have a gummy worm in your hand and you pull the gummy worm with so much force, it doesn't break, but when you take your hands off of it, it is a little bit longer than when you started. That means you have pushed it to the yielding zone. It is no longer elastic. The definition of elastic means that you have to pull the gummy worm, and when you release your hands from it, it comes back to the exact same length that it was originally at, meaning no permanent deformation. So that's very important. I'll add that here to elastic. No permanent deformation when force removed. Okay. All right. So the stress that causes yielding is called the yield stress. Sigma y. And we call this, basically, this permanent deformation, we call this plastic deformation, meaning it's not reversible. This is a point of no return, okay? It is not reversible once the load is lifted, okay? All right. The third section we have here, let's use this color here. We call this third section strain hardening. Okay. Basically, here, let's come to our note area. Strain hardening means that yielding is over. we're no longer able to increase our elongation without causing any stress. And now the stress is going to significantly increase. Okay, so it's going to increase, so we can basically increase load results in increased stress, okay, until a maximum stress is reached, okay? And this rise in the curve is called strain hardening. All right. The last portion we have is called necking. Okay, oh, and also I should point here that we call this the ultimate stress. Sigma U. This is the max stress that we'll ever see, okay? And in necking, we call this our failure stress. This is where it ultimately fails, okay? Okay, so let me come back here. 4, we have necking. Okay, and what this is basically as our specimen elongates, so this picture here, as this gets bigger when we're pulling on it, as bar elongates, we see a decrease in cross-sectional area, and we kind of talked about this already. If I pull on something, that cross-sectional area is going to decrease, okay? And after the ultimate stress, that cross-sectional area becomes localized. So we'll see something like this. If this was our initial shape and we're pulling on it, what we're going to see is basically we're pulling so hard and we kind of get this decrease that happens right in the middle there, okay? So we see this localized decrease, and we call this necking. And this is when this ultimately leads to failure. This is where it fails. So if you keep pulling on the gummy worm, it's going to kind of break in the middle if you have equal force applied on both sides. Okay. All right, so now a couple of things to note. This is a conventional stress strain diagram for a ductile material, okay? Steel is a ductile material. This is very important. Okay, what that means is it gives us a warning before it just kind of snaps, like the gummy worm. Okay, we're able to elongate it and pull and pull and pull and pull, see the deformation, see the necking, and then it snaps. Whereas a more brittle material would be something more typically like concrete, where you'll see cracks, but it could have a straight failure, so a much smaller point of yielding or strain hardening you would see in a concrete stress strain diagram. So this is for a ductile material. And a lot of times we prefer to design buildings or systems with ductile materials, not all the time. Okay, we do use concrete a lot, but ductile materials have their own special place kind of in the code. Okay, so here, oh, I think I wrote all of that in, all of this stuff was for this information here. So you can put that in the slides, but now it's just on one slide. But I'll use, let me see if now I'll scroll down through this. Let me see. Okay, let's look over these slides. So we talked about this. We use the original area, A naught, okay? So one thing to note here is typically we try to stay in the elastic range most of the time, okay? And so we're not really getting to the point where we're even hitting past the yield stress or the ultimate stress, and we don't want to get to failure, but a lot of times we will design inelastically. And one other thing I want to note on this diagram is that this is called, this right here, right? This is elastic behavior, and all of this is plastic, meaning there's no return after you start deforming in that area, okay? Okay, This is the picture from the book that we kind of just recreated and talked about. So this is a reference for you. It has all of the stresses on this side and everything that's kind of going on, and probably a little better picture than what I was able to draw. Okay. So now let's talk about material behavior under stress and strain. So again, we have these two types of categories for materials. We have ductile materials and brittle materials. Okay, an example again is steel for ductile material. And you want to think of a rubber eraser, a gummy worm, those kinds of things. Brittle material doesn't give you as much of a warning, and you want to think of kind of just snapping a tortilla chip in your hand, okay, or breaking a glass plate. Okay, so materials that experience large deformation before fracturing gives you kind of a warning. Steel is an example. And basically we can measure this ductility. We call this percent elongation, and it's equal to L final minus L initial over L initial times 100%. Okay, this is typically 38% for mild steel. Okay, and we can also measure the percent reduction in area. As A initial minus A final over A initial times 100. And this is around, wow, my handwriting is getting terrible right now. Okay, we'll say it's around 60% for a mild steel. Okay, and these are both measures of ductility that we have. Okay, here are some other ductile materials. We're now looking at the elastic region here, and basically this is an example of aluminum. So we don't always have a very well-defined yield point, and there are some things that we can do according to the code and some other empirical estimates to figure out what a yield point is for a metal that we haven't really been able to get a good estimate for in the past, okay? So what we do, if we don't know the yield point, we use something called the offset method, okay? And what that is we typically choose 2% strain, okay? So we come here on this diagram, and we're gonna go to the point of 2% strain. So we measure 2%, which is right here, and we draw a line that has the same slope as the initial line. So here, this is the initial line. We draw a line exactly with the same slope at 2% strain, okay? And we then horizontally measure from the point of a curve there, and we say, well, that's about 51, so we're going to take the yield stress at that point to be 51, okay? So, and again, we call this the offset method. Where is it? Yeah, the offset method. This is when we don't know the yield strength. Okay, so yield strength is not a physical property. It is whatever stress level causes a specified permanent strain, okay? So again, I kind of already talked about this. We assume for this class and the majority of applications that your yield strength, yield point, elastic limit, proportional limits all coincide. So we kind of get to simplify that drawing into this. Elastic, yielding, ooh, not that, ultimate, failure. Okay, it's a simplification. Instead of having to kind of zoom in here and really look at all this stuff going on, we just assume that this is what's happening, and that's what we're going to do for this class. Okay. Now, another material that's moderately ductile in most cases is wood. Okay, and what we do for wood is we design this to respond elastically. And the strength of wood can depend on several factors: moisture content, age, arrangement of the knots, to some different types of things, different types of timber that we can use. And it's generally stronger in compression than tension, okay? And this is kind of a unique feature of wood or timber, is that it's different, it has different strength in each direction depending on the grains, depending on the orientation of the grains along that wood plank that you're using, okay? So you can kind of see here is an example of wood. We have compression and tension inside. These are forces that are applied parallel to the grain as opposed to compression and tension applied perpendicular to the grain, okay? So here, again, this one would, oops, come back here, okay. And then this one here, we show that the strong way of doing this would be applying it parallel to the grain, whereas the weaker way of doing this would be perpendicular to the grain. And then we also have the same thing, shear parallel to the grain is weak now, and shear perpendicular to the grain is strong, because the grain is going to help us not be able to kind of shear those surfaces apart. Okay. Okay, so now we know a little bit more about ductile materials, and we can talk about the opposite of ductile materials, which are brittle materials. Okay, these types of materials tend to show no yielding before failure. Okay, and they don't have a well-defined fracture stress, so it's sudden and we don't have much of a warning. Okay, compared with tension, brittle materials do have high compressive strength. So our very favorite brittle material is concrete. Okay. Oh, I put that right here. Okay, so it has a high capacity for compression, but a low capacity for tension. So the question here is, how do we build so many structures with concrete if it performs so poorly in tension? Okay, what do we do to concrete to help it in tension? Okay, so what we do is, let's say this is a concrete beam, right? We build a lot of parking garages with concrete beams. And we're applying some load. Okay, this causes the system to bend and deform, right? What happens is the top is in compression. That's okay, concrete's great at compression, but the bottom's in tension. How do we help the concrete out? Well, we come here and we add steel rebar at the bottom of the concrete where we would have tension, and because this is steel, it reinforces the concrete. So that's why you'll see your concrete design class is actually called reinforced concrete. So we're mixing these two materials, and we'll actually have a problem later on where we have to solve for some reinforced concrete and design some elements of that. Okay. Okay, so stress strain characteristics of concrete depend on the mix, right? Has to be certain parts water, admixtures, cement, you can have aggregates, you can have fly ash, you can have all this good stuff to kind of make your concrete perform better, stronger, okay? And material behavior is dependent on many factors, and even in some cases, ductile materials can act brittle in certain situations. So, for example, low temperatures, materials become harder and more brittle versus high temperatures in the heat when they become softer and more ductile. Okay, so these are all things that you have to think about in your design. Okay, so now this is super important. We're going to talk about Hooke's law. So, Hooke's law allows us to analyze that linear portion of the stress strain diagram. Okay, so you might have already seen Hooke's law as F equals Kx for springs. This is one of Hooke's laws. And this is a similar one. It's also a linear relationship, proportionality between the normal stress is equal to E times epsilon. Our E is called the modulus of elasticity. Okay, and what that is it's the slope of the stress strain diagram of the linear portion so just rise over run, right? So if this is my diagram, let's say this is a linear portion, right? E is just this slope. Okay. Okay. Another word for modulus of elasticity is Young's modulus. And the units are PSI, KSI, pascals, kilopascals, etc. Okay. For steel, a commonly used E value for steel is 29 times 10 to the 3 KSI. So you'll see that a lot in steel design. This is equivalent to 200 gigapascals, something like that. Okay. Okay. If your E value is not given, they might tell you it's, for example, A992 steel or A36 steel. You would just go to the table in your book or to Google and you can get the E value accordingly. So either it's given to you or you'll have to calculate that, okay? Okay, so this indicates the stiffness of our material. That's why we call this Hooke's law, because Hooke's law, F equals Kx. This is the stiffness of a spring. We call that the stiffness, right? So E indicates the stiffness of that material, how brittle or ductile it is, okay? E can be only used, Hooke's law actually, not just E. Hooke's law can only be used in the linear elastic range for material, okay? And here, again, this is just different modulus of elasticities for different types of material. I'll let you guys look over that on your own. Okay, let me see how much more we have, and we'll put this into 2 videos, quite a bit. Okay, so let's stop this video here, and we'll continue with the next video and talk about strain hardening.